Yes, go ahead and share your screen. This will be loud enough. Okay, we see that well. Go ahead.
Okay, let me just test if. Wait a second.
Carl, could you speak up? Actually, I don't understand your question.
Oh, the last presentation was I can see your screen. Maybe I missed it and there wasn't a PowerPoint, but now I can see. This is fine. This wasn't,
Okay.
the sharing didn't happen for the last presentation.
Oh, my apologies. We could see it in the room, and I guess I forgot to cast it on Zoom. Sorry about that.
That's okay.
Get my attention if something weird happens by talking. I'm not watching chat as closely as I ought to. Go ahead, Chloe.
Okay. Hi everyone. My name is Chloe and I'm from Macalester College. Today I'll be sharing with you a project that we've been working on for the past couple months for this year's Midwest High Power Rocketry Competition. So this year we have the Precision Landing Challenge. This is the poster that we made in early 2022 fall when we wanted to recruit members for the team. And so the goal for this year is to, well, first it's precision landing, which means we want to land our rocket in a specific destination. We also have other goals like vertical landing, which means we want to land our rocket vertically. And then we also have a requirement of using a self-designed sensor suit to collect flight data. And then there are also other hardware and flight requirements. But today I'm just going to focus on the precision landing because that's like the main focus of our work. So first of all, the way that we wanted to achieve this precision landing is by controlling its landing trajectory, so that means instead of using a regular traditional circular parachute, we want to use a parafoil instead, because a parafoil is something you can control its horizontal moving direction. So because the parafoil is in this rectangular shape, you can, by pulling the control lines, you can control how each side of the parafoil deflects. And so that creates a asymmetrical structure, which means the forces on both sides will not be balanced. And that means you can create a turn. So you can turn right or turn left. And that's how you can control the horizontal moving direction with the parafoil. And so another benefit of using a parafoil is that because it has a larger reference area than the traditional parachute, and also it's affected by the lift force during the flight. A parafoil should descend at a slower rate than the parachute in the air, which means it allows for more time for us to control the motion in the air. Yeah, and then to implement this design, we essentially want to use linear servos, which is I have this like short video of a linear servo working. We want to use linear servos to pull up and down the control lines. So we will have two linear servos controlling left and right side of the parafoil. So we have this. So we have a parafoil, and then we have a left linear servo and a right linear servo. And because we expect the system to be automated, which means we want the system to drive itself to the destination, which means we're not remotely controlling it. So we want to connect our linear servo with the Raspberry Pi, which is essentially just a computer. And then the computer is also connected to all of our sensor suits. So it has access to all of our sensor data. So we want to implement an algorithm to the computer. So the computer will take in all of the sensor data and then make decision on how much it wants to turn, maybe it wants to turn left or right, and then it will then send a command to the servos to tell them how much to move and what direction to move. And so essentially it's kind of like a human brain trying to decide how to steer a paraglider. And so that's the general design on our physical system. And so here is a picture of all of our electronic system. On the left is our linear servos, and then we have 3 boards. The lowest green ones are Raspberry Pi, and then the servo hat is to connect and control the linear servo. And then on the top, we have this one board that has all of our sensors, which is called a Berry IMU GPS sensor. Yeah, so that's our physical system. And now we want to do some theoretical modeling with the parafoil because first of all, for our previous competitions, we usually use software like OpenRocket just to demonstrate flight simulations. So we know how to use those softwares. So we never need to learn all of the specifics of the aerodynamics of the whole entire flight. But if we're using a parafoil instead of a parachute, we can't really rely on these softwares anymore, which means we need to study the aerodynamics of the parafoil to know how it flies in the air and to understand how the control works. And so we also want to make reasonable estimation of its flight performance. So there's a lot of need in studying the theoretical model of a parafoil. And so here is a breakdown of the structure of the parafoil. We can basically deconstruct it into individual panels and calculate the forces on each of them. So when one panel is deflected with a certain angle, the forces that act upon that panel would change as opposed to when it's not deflecting. So one side is not deflecting and one side is deflecting. And so we can calculate the forces on all of them and then evaluate the effect of deflection by calculating motion parameters of the parafoil, which means we can calculate acceleration and velocity based on the forces that we get. So the technical advisor of the competition helped us to find this paper that analyzes the parafoil and payload system, which is really helpful and pretty much exactly what we want for our model. So we have been reading and studying this paper and trying to recreate a model in this paper so we can build our own analysis upon it. So this consider it as like a prototype of our model. And so the mathematical work here, which is basically the result of this paper, is basically constructing these 2 tensors, constructing this left rank 4 tensor and then this vector on the right. And so eventually we're solving for this 12 times 1 vector, which gives us acceleration in 3 different directions. And so once we know the acceleration, we can know the rest of how its motion goes, and we know specifically what kind of parameters creates a turn, how much of a turn it is, and then just to dig into the details of its flight. And so here are the next couple slides is our current results. I deflected the right wing so you can see its acceleration is moving towards right, and with the larger angle of deflection, you are actually moving towards more right, which is exactly what we expect. And so this is with different angles of attack. This is with degree of 8, 10, and 12. I'm just gonna quickly skip over this part. And so we use the drag and lift coefficients used in the paper, but that creates a problem because these coefficients are pretty much unique to each individual system. which is why this model is still kind of like a work in progress, because we still need to adjust a lot of our parameters, and then we need to find more realistic parameters that's specific to our own system. And so that will help us produce more reliable results. But we got the basic structure figured out for now. And so the next step to do is just to try out with different parameters. Another work in progress is our algorithm. So we're currently trying to integrate all of our data from all of our sensors. And then we want to design an algorithm with limited data, because the theoretical model requires so much output. It's just impossible to recreate that theoretical model within our algorithm. So the next step is for us to figure out how does the computer decide with limited data, like only with the location and acceleration data, or angular rotation data. Yeah, that's all. Thank you.
Okay, thank you. Let's take questions. In particular, questions from people who are in this competition, who are trying to also solve this same problem. Kelly.
What materials are being used and what stitch pattern are being used?
Okay, so the question is what materials are being used and what stitch pattern this is, what material and stitch for the parachute. It's the parafoil itself.
I don't really understand what its stitch pattern is.
Well, let me phrase the question slightly differently. Are you purchasing or are you sewing this parachute, this parafoil? Or are you
We
buying?
directly purchase products, so we didn't make the parafoil ourselves.
Okay, so basically, where did you buy it from?
Sorry, I don't remember.
Was it Apogee Components, perhaps?
We bought a couple different parafoils, and we're still in the stage of trying to decide which one to use. So I can't really have a conclusive answer on that, sorry.
No, that's fine. I know that some teams, including the one here, is trying to make the parafoil, as are you. And so that's a great question. You should maybe talk to my students as opposed to people like Hamlin or people like Macalester who have purchased products and know less about the thinking behind them, maybe, but are certainly trying
Yeah,
to.
we're a very small team and we don't really have time for that kind of task.
Well, that's great. This is actually sounds good. I'm glad that you're working hard on it. Other questions from the audience or questions from Zoom? Yes, go ahead.
How can you determine how big is the span of the parafoil that you need for the rocket?
Okay, so the question is, how do you determine the size of the parafoil that's needed, which presumably is related to the size or the weight of the rocket?
So in our theoretical model, you basically enter the numbers of the area. So we just, we can estimate what, based on the speed and the terminal velocity that we want. It kind of works the way that a parachute works. It's just that the calculation is a little bit different. So we just test it in the model and to see which one gives us the best result.
So I'd say it's useful that you have access to this one paper, and presumably there's more than just one paper out there. But yeah, I don't think OpenRocket or RockSim will allow you to put in this kind of parachute into that kind of simple simulator. So
yeah, it wouldn't be accurate. Sorry.
Yeah. It's more efficient than a regular parachute because it has the wing lift as long as you're moving forward. Time for one more question from the room or from Zoom, Dave?
I'm curious about whether this parafoil is stabilized in a certain orientation relative to the wind, so that you are controlling the direction perpendicular to the wind, or is it does it randomly orient the wind such that you're trying to shift left or right? It would depend on orientation.
Okay, so just in case you couldn't hear quite all of that, he's curious if it's windy, if the wind is blowing in a specific direction, does this device try to fly into the wind or fly away from the wind or completely doesn't care about the wind?
Yeah, we don't really know how the real scenario would be, but in the model, you can simulate different parameters of the wind speed and in all different directions, and then it will just calculate for yourself, and then you can see how it moves.
Okay, I have actually one final question, sorry. You probably said this and I missed it. Are you controlling this by radio from the ground, or this is being calculated and tried to control autonomously in flight?
It's trying to drive autonomously.
Okay, test.
yeah.
So thanks. Another round for our speaker, please.
Thank you.